Welcome back to this lecture series. Today I would like to introduce to you the convolution integral, which forms one of the fundamental techniques in transform calculus. In the context of the Laplace transform, let us define the convolution integral. Let f of t and g of t be two functions we define the convolution of these two functions or these two signals as f of t star g of t given by integral 0 to t f of u into g of t minus u du or integral 0 to t g of u into f of t minus u du. So you can see that there is a commutative property here. Therefore, we can also write this as g of t star f of t. So the star symbol denotes the convolution operator, and this is what we call the convolution integral. For example, if you want to calculate e power t star 1, so that is a convolution of two functions e power t and 1, you can evaluate this as integral 0 to t e power u into 1 du. So we are using this definition. Because f of t is equal to 1, f of t minus u will also, because g of t is 1, g of t minus u is also equal to 1. So you integrate that function and apply the limits, and you will get e power t minus 1 as a convolution of e power t and 1. Please observe that the output of the convolution operation is another time domain function. Therefore, convolution is a time domain operation. Now, our next focus is going to be how the convolution becomes very important in the context of Laplace transforms. So let us see that in the next case. Okay friends, after having defined the convolution integral, let us see how the Laplace transform makes things very simple about convolution of functions. The Laplace transform of the convolution of two functions is simply the product of the Laplace transforms of the functions. So what is f of s here? This is the Laplace transform of f of t, and this is the Laplace transform of g of t. So it's a very elegant theorem which says that if you take the Laplace transform of the convolution, then it is simply the product of the transforms of the individual functions. Let us take a simple case. Suppose we would like to compute e power t star sin t. So we are here. We can define f of t as e power t, g of t as sin t, or vice versa, because we know the convolution operation is commutative. So if you follow this definition, then this is nothing but the Laplace transform of e power t multiplied by the Laplace transform of sin t. So this is 1 by s minus 1 into 1 by s square plus 1. So the output is 1 by s minus 1 into s square plus 1. So the biggest benefit of the convolution theorem is if you can identify that it's a convolution product, you have to simply take the algebraic product of the transforms and you get this particular result. However, in an exam like GATE or an advanced national level exam, You never get questions so directly. So let me tell you how the same question would be designed in a competitive exam. So let me write it as an alternative way of questioning. Same question put in a different way. So Laplace transform of e power t into sin t could be asked as integral 0 to t e power u into sine of t minus u du. Please recall the definition of convolution integral. F of t star g of t is f of u into g of t minus u, integral 0 to t. So if you are given this, you must immediately be able to map it onto e power t into sin t, because both of them are one and the same. This is a symbolic form, but that is the integral form of the convolution. Therefore, the answer to this would be straight away this one. Both are one and the same. So from here you go here. So in fact you can do like this: come here, and come here. So if you are having sufficient practice, then you will know this is equal to this, and you can directly write the output like this. But this is the sequence in which one has to proceed in order to produce an output. Please observe, whether you do like this or like that, it just takes couple of steps, which means about 20 to 30 seconds, not more than that. That's exactly what we want to have in this particular format of exams. So one must be very quick enough to know in which context the question has been framed and immediately connect it to a property, and then see how quickly you can reproduce the output. So it's all a question of knowing your principles and how efficiently you have practiced it. After all exams are nothing but managing time. So I hope you're all be able to understand these very fundamental points. After this, let me introduce to you the unit step function, which is also known as the unit impulse function. Okay friends, one of the important functions in signal processing is what we call the Heaviside's step function, or what we call the unit step function. Now let me show you the graph of this function, then give the mathematical definition of that, and then sufficiently let me write the Laplace transform of that. Now what we call the second shifting property of Laplace transforms is based on this function. We know that whenever we have electrical circuits and the driving force is not always a continuous function, then one has to analyze that particular circuit in terms of Laplace transforms. The classical methods do not address this problem. So the Laplace transform is the best tool available for all functions where there are finite number of discontinuities. So unit step function is one such function. So let us write the definition, but before that let me draw the graph for you. This is the time axis. Observe the notation. This is the unit step function definition. Sometimes you can also use ut minus a, but I think this is more popular than that one. Right. Now what is this definition? On the time axis, let us say a is a value. This a is this. Now after a there is a jump, and what is the height of this jump? It is 1 unit. So there will be no signal between 0 to a. Then after a there is a unit jump. So there is a discontinuity at this particular point. So therefore the unit step function is not continuous at the point t is equal to a. And because it is just a unit jump, finite jump, we say it is not a jump discontinuity. Jump discontinuity means a discontinuity where suddenly the graph shoots off to plus infinity or minus infinity. So definitely there is no jump discontinuity here, but there is just a simple finite unit step steep. So therefore this is the definition of the or the graph of the unit step function. So very easy to write the mathematical definition. The definition is unit step function is equal to, it is 0 in this interval, that is 0 less than t less than a, and after a, that is for t greater than a, it is 1. Right? Now when you find the Laplace transform of this function, you have to integrate only in the second interval, a to infinity 1 into e power minus st dt. We don't have to integrate over the integral 0 to a because there is no signal value in that interval, 0. So therefore, it is only in the second interval that we integrate, and you will simply get e power minus as by s. So the Laplace transform of the unit step function, okay, the ideal unit step function is e power minus as by s. Now I'll be interested to handle situations where we have rectangular pulses or a pulse train and things like that. All these problems can be effectively solved using the unit step function. So in my example that I'm going to take up now, I will take a simple rectangular pulse and show you how the Laplace transform can be calculated. Now let's take a very simple situation where I am taking a rectangular pulse and I want to find its Laplace transform, right? So the signal that I have selected is the time axis. This is the function. Let us say this is 2 units and this is 4 units, and I have got a simple rectangular pulse. The height of this pulse, let us say, is some 6 units, right? Now for a situation like this, if you want to find the Laplace transform, right? So the question is, what is the Laplace transform of the signal? We want the Laplace transform of this signal. Two approaches are possible. One thing is using the definition of the transform, 2 using the unit step function. So the student can use any one of these methods, depends upon how well he has practiced one of the techniques. So method 1, we can write f of t as, the amplitude is 6, so 6 times u2t. So the unit step function with discontinuity at 2 minus ut4. I think the student can very easily understand how this has come. So from the ut2 signal, if you subtract a ut4 signal, you will be left with the 2 to 4 band with amplitude 6 units. So the Laplace transform of this function will be 6 times Laplace transform of ut2 minus ut4. So this will be e power minus 2s by s minus e power minus 4s by s, which you can write as 6 by s times e power minus 2s minus e power minus 4s. So this is how you can get the Laplace transform if you use the unit step function definition of the signal. Now here I will show you how the integral definition will also help. Method 2. Here you don't bother about unit step function, you only integrate from 2 to 4 e power minus st into this function, that is a constant function at a height of 6 units. So it is nothing but 6 times e power minus st dt. So if you integrate that and apply the limits, you will get back this answer. So the student is free to choose, either he can go for direct integration or he can go for a unit step function type of technique also. It all depends upon practice. Okay, before we launch on to problems, I would like to introduce one of the another important functions that we commonly see in signal processing, that is known as the unit impulse function, which is also called the Dirac delta function. So let me write that for you. Now this is a very important function, particularly when we are dealing with functions, which excite circuits which have that spike like behavior. Okay, so how does the graph of this look like? Let us first draw the graph, then write the definition, write the Laplace transform, and then see if anything is there to be observed. So this is the time axis, and observe the notation. Now delta t denotes the impulse function, that is epsilon. All of us know in the language of mathematics, epsilon is an extremely small interval. Okay, so suppose we take this as a small interval of time. Now in a enlarged or expanded form, it's highly magnified, but in practice this is an extremely small interval. So you define the height of this rectangle to be 1 by epsilon. This width is epsilon. You take the reciprocal of that as the height of the rectangle. Now you can find that the area of this rectangle is exactly 1 unit. That is why it is called the unit impulse function. Okay. Now if you have to write the definition of this, it is 1 by epsilon in this interval, 0 less than t less than epsilon, and beyond epsilon it is 0. So the signal content is only in this interval. Beyond that we don't have any signal content. So this is the definition of the impulse function. Now if you want the Laplace transform of this, Laplace of the epsilon function, you have to only integrate in this interval 0 to epsilon into 1 by epsilon e power minus st dt. So this is straightforward integration, e power minus st by minus s from 0 to epsilon. So what is that you will get? You will get 1 minus e power minus epsilon s by epsilon s. So this is the Laplace transform of the impulse function. But as I told you, epsilon is a very small value of time. In fact, if you put a limit on that, okay, I will write that special case here. As epsilon approaches 0, so let us observe this limit as epsilon tends to 0. E power 0 is 1, so 1 minus 1 becomes 0, and again epsilon tends to 0 makes it a 0 by 0 situation. All of you are familiar with the L'Hospital's rule. So when you apply the L'Hospital's rule on this, so the Laplace transform of delta t as epsilon tends to 0 is equal to limit epsilon tends to 0, 1 minus e power minus epsilon s by epsilon s, and this will be equal to 1. I will just write for you L'Hospital's rule. Details you can work out, but that is a very, very important transform under limiting conditions. So in fact, one has to always remember three important things in the context of Laplace transforms. One is the convolution integral, two is the unit step function, and three is the impulse function. These play a very, very important role in signals and systems, and subsequently in an advanced paper like digital signal processing. So let us now get into the problems and see how our knowledge can be applied to different contexts, and let us go systematically so that the moment the question is seen, you will know which property is being used or what is there in the mind of the examiner when he sets this question. So let's get into problems.